Now we'll hand it over to Hughes, who will tell you a bit more serious things on design of experiments and statistics.
Thank you very much, Jan. So you presented a very interesting examples. Actually, we've got helicopter, we've got classic car, we even got hot dogs. But I'm a bit disappointed because you did not highlight much that all this relies on a really strong theoretical background. So I will have to be the bad cop, and I will have to make it quick. So let's say that if you would like to lead experiment or computer experiment, you will have to make a smart design of experiment. Here is a quick history of what has been made and how it has been generalized to computer experiments, so-called simulation. Regarding design of experiments, design different experiment purpose, you can find something we already described in this presentation earlier, is about screening variables. So it's making sensitivity analysis in order to find what parameters are responsible for the main effects and what are the most important interactions between factors to take into account into a system behavior. And second application we can lead for experiment is about making design space exploration and prediction, and finally optimization. So here is what is the design of experiment meant for. The idea of a design of experiment is about trying to maximize learnings. It means maximizing the total experimental variance, while trying to control the variance of factors that are not interesting to us, and of course trying to minimize the random error variance that is inherent to all physics experiments. And we are trying to maximize learning while, of course, trying to using a minimum of resources, trying to make at least tests as possible. So some classic design that you might know are about factorial design. Those are quite easy to construct, and from those you can pretty much gather every effects. But of course, the main drawback of it is that you are running a lot of different runs, so it's quite expensive when you have to study a lot of different factors. A cheaper solution would be to run a fractional factorial design, so just making some what we call aliasing structure, trying to, for example, in this case, predict the behavior of factor x3, saying it could be the interaction effect between x1 and x2. So this is of course cheap, but the fact is that you are confounding main effects with interaction effects, so might not be relevant in all cases. And
I love
some
this one. It's blue and
this was okay.
it's blue and orange.
Okay, it's corporate colors, sure. So well, actually, another design that you can use. Those are let's say the most optimal one if you would like to make some screening analysis, because it's minimum of run for gathering every main effects, but actually they does not exist for every kind of experiments. Here you got for 12 runs. I guess you got one for 23 runs. So you can't actually make a Plackett-Berman design for every experiment. And considering optimization objective, you can the classical way to proceed with an experimental system would be to first run screening analysis in order to just focus on most interesting factors. Then try to make as you would make a linear approximation. So make steepest ascent method on linear first order actually polynomial model. And when those models are proving some lack of fit, meaning that actually you've got too much curvature to be approximated by a linear first order polynomial model, you can finally try to model your function with a second order polynomial model and run your optimization analysis. So this was for physics-based experiment, how we can relate on our side in ESI for simulation. Actually, it would be quite the same, just that as physics is non-deterministic, simulation is deterministic, but just proving some numerical noise. So random error has no more sense for simulation. Just you only got the simulator bias. Actually, that would be about a lack of accuracy in the model implementation. And some techniques that you use for physics experiments does not have real sense, such as randomization, replication, and blocking. Instead, what would be relevant for computer experiment would be to make space-filling design of experiments. At this stage, I only presented you 2 levels or 3 levels, factorial design or fractional factorial design. This is useful for experiment when you almost know the trend of the behavior of your system, but in simulation, the idea is that you don't know the behavior of your system, so you will have to put more point within the design space. And the idea then is to try to, depending on the objective you've got, trying to set the most smart and most cheap design of experiment as possible. So here you got a quick review of the different modern design of experiment, depending of if you don't know at all any information on the system. So it's about system-free design techniques. The idea would be to just make as uniform sampling as possible. It's the case for light in hypercube sampling. You also got system-aided sampling techniques. So when you've got some information on your system and then you are trying to incorporate it in your design of experiment. And finally, you've got adaptative techniques. It's about just making run after runs and deciding after one runs what would be your next sampling techniques. So here it's 3 typical workflow to make design optimization. First is a simple one, trying to build let's say a surrogate model that is as much accurate as possible on all the design space and run optimization on it. This is quite costly. So another technique would be to sample your design space and change your meta models depending on where the optimum could be. And it's quite the same as the next the last techniques. So finally, to be able to run your design space exploration, to be able to run your optimization, you will have to go through surrogate modeling pretty much every time. And here are some techniques that you all know and that we are working with within Scilab. So first and second order polynomials regression. These have some benefits. Of course, it's quite easy to construct and quite easy to go more accurate, but I would say that is more unreliable than interpolation techniques. About interpolation techniques, you got radial basis function. Here is the formula you've got with some kernel function, typical kernel function that could be tuned. You also got Kriging as interpolation techniques. Oh, you like it?
I like the representation on the right.
Okay, so Kriging seems to be more accurate for nonlinear problems, and it gives some benefits about statistical interpretation, but it's actually quite hard to obtain.
What is the gray representation around?
Actually,
the
it's the uncertainty you are trying to model your Kriging with.
Right.
Yeah, that's
great.
Jan already told you about model-based surrogate modeling, such as POD or as Paco is trying to do PGD. It's currently doing actually. You also got some machine learning-based technique. Finally, that could be about just classification if you got some categorical response, or about regression. So here it's support vector regression, using trying to create an hyperplane that would maximize or minimize the distance between some support vectors, using the trick of kernel in order to try a higher dimension space where you can find a linear
dimension. It's 10 in the morning, higher dimension.
Actually,
You want us to jump in the mattress?
Yeah,
Matrix,
exactly.
right?
Actually, could be quite high and could be quite hard to understand too. And
Wow.
finally, of course,
Neural networks.
everyone is talking about, even if it's not really, I would say, effective for optimization case. But anyway, if you are interested in, you can, of course, use neural network training.
Yeah. Well, looks fancy, right?
Yeah, looks
It's
quite
quite
messy.
gotta be good.
Yeah, sure.
All right. Yeah, I mean, neural networks here. One case of function approximation as we addressed early on CFD data. The same one, you can have a look at it also on our website. As I told you earlier, you get all of the tutorials. There's some on machine learning. You can go have a look at it if you want to discover what machine learning and logistic regression, artificial neural networks obviously is about, deep learning even. Wow. That's a bit too much for today. We'll probably stop it now before we say some insanity. And if you want to dig deeper into the sources, we have a lot of tutorials on data mining, data fitting, classification, neural networks, blah, 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 all of this. It's amazing. So thanks for bearing with us.
Thank you.
No, not for you, not for them. I don't know if they're still
Really?
up. But if you now have questions, we are very happy to answer them if we can.